Um, Good morning, everyone. We are pleased to have Ruth Marie Clay to speak to us today. Ruth did her PhD in UC Berkeley and is now a professor in UC Santa Cruz. Her expertise is in the formation and evolution of planetary systems. She works on a broad range of topics. Some of them include planetary atmospheres, orbital dynamics, and pebble accretion, which we will hear more about today. During the talk, if you have any question, please use the raise hand function or notify me in the chat. My name is Jeffrey, and I will find a good time for you to ask your question. So with that, welcome Ruth, and please take the floor.
Thanks, and thank you for having me. Yes, today I'm going to talk about two ideas, two thoughts about the origins of structure in interplanetary systems. And like many people, one of the motivations that I have, though not the only one, for studying planetary systems is to ask the question, is Earth rare? But of course, on the way to that question, we first need to answer, or at least we also need to answer the question, is the solar system rare? And by that, I mean, is the structure of the planetary system that Earth resides in a common structure in the universe? And we need to know that both because that impacts the history of a planet that forms within its system, its formation environment is going to tell us something about its composition, perhaps its dynamical history, things that might have happened in its past, but also because, as we all know, it's difficult to see Earths so far. And so one of the biggest clues that we might have about whether a planet might be something like Earth, rather than just the size of Earth at a location like Earth, is whether it formed in a similar environment. Also, planetary systems are just cool physical systems. So that's the other reason I like working on them. So I want to think about this. Is the solar system rare? And what sets the structure of the inner regions of planetary systems? And just as a reminder, let's think about the planets that we know orbiting other stars so far. If we look at these on the left are planets that have mass measurements as a function of their orbital period. On the right are planets that have radius measurements. And we can break these up into gas giant planets. So if we look at this red line here, this is the orbital period of Jupiter. Most of the gas giant planets that are currently observed have mass measurements. They're found with the radial velocity technique, but they're mostly with orbits interior to that of Jupiter. And that's largely, though possibly not entirely, a selection effect, but it's mostly a selection effect. If we look down at planets with the mass or size of Earth, there's not a whole lot there. That's definitely a selection effect. And then if we look on the right at these intermediate sized planets, which are mostly in the radius plot because they're mostly found with the Kepler satellite through the transit method, we see a large collection of super Earth planets. So things with radii larger than the Earth, but that are smaller than gas giants. All right. So if we think about how we think planetary systems formed, there's long been a classic framework for how that happens. And it starts with molecular clouds like this image of the Orion Nebula, where you can see in these insets, protoplanetary disks forming around young stars. And in those disks of gas and dust that are forming around young stars with material falling onto them from the nebula, you have gas, dust, and ice in the outer regions. You have gas and dust in the inner regions, and this is the site of planet formation. In those disks, if you have a lot of material, if we can think about what kind of planets formed, at least in the classic pre-exoplanet models, as being largely a function of two parameters. The first one is how quickly they grow, and that is depends on where you are in the disk. So if you're closer to the star, your orbital time is shorter. That means your dynamical time is shorter. That means you grow faster. And if you're farther out, you go slower. And also, of course, if you have more material, that means you're going to grow faster. So a more massive disk will grow faster. And this leads us to the classic view of how planetary systems formed. This is developed for the solar system, and it works incredibly well for the solar system. And that is, in the inner disk, there's not a lot of material. There's only dust. Ice can't form, and also just the area in this region is pretty small. So you make puny things like the Earth. And you go a little bit further out. Now you can make ices. The area of your circle is bigger. Now there's more material available. You can grow larger solid cores. And if you make a large enough solid core, then it can accrete an atmosphere with a mass comparable to itself, which now makes it twice as massive, and it can accrete an atmosphere with a mass comparable to itself, and you get exponential runaway, and you can form gas giant planets. You go yet further out in the nebula, and you can make these large solid bodies, these ice balls, like the ice giants, but now you've taken such a long time to do it that you're not able to accrete enough gas to be a gas giant before the nebula dissipates, and you end up with an ice giant in the outer disk. Okay, so that all makes sense. Of course, it's not, this exact picture can't explain the systems that we see in extrasolar planetary systems, but many of these concepts, of course, still apply. And let me just dig a little bit deeper into this classic theory of planet formation, because these ideas are going to come back later in what I'm going to discuss, and talk about the concept of the isolation mass. And that starts with the Hill radius, which is the radius around a planet where a tidal acceleration from the star balances planetary gravity. And inside that radius, or the Roche-Lobe radius, of course, that's where you can have a moon orbit around your planet, or we often say that the planetary gravity dominates over the gravity of the star. If you go ahead and insert a Hill radius into a protoplanetary disk, then if material can't be replenished, then typically what you get is that a solid core can at most accrete material from within several Hill radii. That's its region of gravitational influence. And when you've accreted all of that material within several Hill radii, you've reached an isolation mass planet, and it can't grow any further. So the isolation mass plays a key role in the classic theory of planet formation, because in the inner regions of planetary systems, your isolation mass is small. That's why the Earth went through a late giant impact phase to complete its growth, is what is thought. That the moon forming impact is part of that late giant impacts phase. But in the outer part of the disk, the isolation mass is just small enough that runaway gas accretion takes a long time. Right? If it took the ice giants grow to isolation masses in classic core accretion models that are just small enough that, given the opacities of the atmospheres, it takes a while to accrete enough mass to go runaway. All right, so that's all very nice. I want to talk about how these ideas are challenged by Pebble accretion, which is an idea that has been talked about a lot in recent years in the planet formation community. And before I do that, I want to just sort of summarize the ideas that we've talked about so far in one possible framework for why you might make different planetary systems around different stars. So really, fundamentally, that's what I want to understand. If you take a star in the sky, what kind of planetary system are you going to make around it? What sets the kind of planetary system you're going to make? What are the key parameters, and what's going to tell us, what kind of system it'll make? So one way you can imagine that, that flows, I think, in a fairly straightforward way from the story that I just told, is to think about, well, it's a function of your disk mass. So if I've made this diagram here, distance from your star, disk mass, it intentionally has no units because we're just trying to see the pattern. And the idea would be that if you have low disk mass, you don't have a lot of material, you make sort of little rocky planets, If you go far enough out in the disk, now you have ice, you can make some ice balls, but they don't get big enough to reach a mass where you can accrete a massive gas envelope and form a gas giant. But if you get to larger and larger disk masses, eventually you'll get to a system where in the inner system you can make our puny Earths. You go further out, you're going to make gas giants, and in the outer part, you'll make ice giants, as in the solar system. And I feel pretty confident that the solar system exists, so I'm happy putting that on this plot. And then you go to larger and larger disk masses. Now you're going to make more massive rock balls on the inside. It's going to be easier to make gas giants, right? Just because there's more material around, so you can make them possibly closer to the star over a wider range. And if you go to larger and larger disk masses, now it might become so easy to make gas giants that you'll make too many of them, and then you end up with a big dynamical upheaval to do, and you get a really big mixture of systems. So why might I put this on this plot? I think there's actually a fairly good amount of evidence that there are systems in this sort of region where you make a bunch of planets and they go dynamically unstable. And one of those pieces of evidence comes from one of the earliest results in exoplanet science, which is this planet frequency metallicity relation, which really, because this is, again, one of the earliest results in exoplanet science, is about very close-in planets. So what this says is that if a star's metallicity is high, then it's more likely to have planets as of 2005. And we can go ahead and look at this in a couple of different ways. If you look at, this is distance from our star. This is a little bit confusing because this is 1 minus eccentricity squared. So down at the bottom is higher eccentricity planets. You can see that both right near their star, the blue points, which are the high metallicity stars, are more likely to be represented compared to the red squares, which are low metallicity stars. I'll do something that's a little more statistically robust in a little while. So if you're worried about that, you can see it. Wait for it later in the talk. But not just right near the star. If you go a little bit further away from the star, the really high eccentricity planets seem to be around high metallicity stars. So this implied to us that why would high metallicity stars matter for these high eccentricity planets? Well, perhaps there's some sort of dynamical planet-planet interactions that's generating this population. And this is really my favorite way of looking at this.
Yeah. We have a question from Daniel.
Please.
Daniel?
Oh, should I just ask it?
Yeah,
sorry, you may be going there already, and maybe this is a distraction, but could you click 2 slides back? I just had a quick question.
Yep.
One more, sorry. So there's this little blue sliver in the phase space between rock and gas giants at the solar system disk mass. Is that just a schematic kind of cartoon issue, or is that a locus and parameter space that has some physical meaning? And Roman was saying that might be asteroids. Could you clarify that a little bit?
Yeah, so this is, so the reason I put that in there is that, it looks like the ice line in the solar system may have been located at something like 3 AU, at least at some relevant formation history, because there's a water gradient across the asteroid belt. We obviously don't have an ice giant in between Earth and Jupiter, but perhaps the ice line was a little bit closer in. So if you had made a solid planet, it would have been made of ice. But that's just speculation. I don't think it's critical for this story.
Okay, thanks. Sorry.
Okay, so sorry. So where was I? All right. So this is my favorite way of looking at this metallicity result. Okay. This is radial velocity discovered planets, just taken from exoplanets.org. And these are the planets around low metallicity stars. And I've grayed out everything that isn't, roughly a gas giant. Okay, here's 1AU. You see a bunch of them here, and then there are a few of them in here. Okay. And here's the one around high metallicity stars. So if you look at the distant ones around 1AU, they're similar numbers around these two kinds of stars. But around the high metallicity stars, there are many more in the inner region. So I'll just put them on top of each other. And so I would argue that the statement that gas giants are more common around high metallicity stars is really a statement that they're more common in the inner regions of the planetary systems around high metallicity stars. So if you go ahead and imagine this low metallicity distribution and just say, well, what if we just had a bunch of dynamical interactions and like smeared this whole thing out, then maybe it would look something like this. So, so either you could say, well, you're more likely around a high metallicity star to form gas giants in the inner system, or you could say that there's some dynamical process that smears them out. It's actually hard to get them from way out here all the way in here without either having some sort of migration or some sort of formation in here. But this is just a much more smeared out thing. You're more likely to have gas giants in the inner regions around high metallicity stars. All right, so, and these planets in here, they all have really high eccentricities. As we all know, they're not on circular orbits, they're on eccentric orbits. So some sort of dynamical interaction is taking place. All right, so that's the motivation for thinking about this part up here. There's some dynamically mixed orbits. So I think that this organization here, where we're talking about disk mass versus distance from the star, it makes a lot of sense. It may well be correct, but this is actually not the organization that you would get if the growth of solid planets is dominated by Pebble accretion, as I'm going to argue. So hopefully by the end of this talk, my goal is for you to understand that statement and think about it.
We have a question?
Yes.
Sukanya?
Hi, Ruth. Quick question about the difference in demographics between the high and low metallicity stars. Is it clear that that's not a selection effect, especially given that that's being derived from RV observations?
So I would argue that there, or at least, correct me if I'm wrong, but I don't think there's any reason why, if you can see the distant giants around the low metallicity stars, you wouldn't be able to see the close-in ones. So this certainly isn't a, I haven't plotted here a statistically complete sample. This is just all of the RV observations. But the argument is that if you have similar numbers out at larger distances, why do you see a lot of the closer in ones around the high metallicity stars, but not around the low metallicity stars? Just the shapes of these distributions are different, and the part that's missing here is the easier to observe part. So I'm not sure how you would make a selection effect that would cause this feature.
Okay.
But if anyone has any ideas, let me know. Okay. Okay. So what does Pebble accretion do for this story? So Pebble accretion, I'm going to use, as many people do, as a term to sort of encompass many things, not just Pebble, well, not many things, two things, not just Pebble accretion itself. The first one is the long appreciated fact that small solid material drifts through the protoplanetary nebula. And the reason for that is that if you have a gas disk orbiting a star, it has a radial pressure gradient outward. So that means that it thinks it's orbiting a star that's a little bit less massive than it actually is. And so it orbits at slightly slower than the Keplerian orbital velocity. But if you have a planetesimal, solid body, it wants to orbit at the Keplerian velocity. It doesn't feel that pressure gradient outward. And so as a result, it feels a headwind from the disk gas, and that causes an acceleration, which causes it to lose angular momentum and drift into the star. And so if you have a big body, that acceleration is small because your surface area to mass is not that big. But if you have a small body, then it's very well coupled to the gas. It feels a large acceleration because it has a large surface area to mass. So small bodies, well, sorry, I should say that again. The acceleration is large, and in this case, the acceleration is small. The drift is maximal where your acceleration is where your size is, where your particle is marginally coupled to the gas. Okay, Pebble accretion, the second process that I'm going to be referring to is Pebble accretion, which is that if you have a solid core and you have a small planetesimal that's feeling gas drag, and it comes into the Hill radius or the region of gravitational influence from the core, then that gas drag can cause it to lose energy, lose kinetic energy with respect to the core. And if it dissipates all of this kinetic energy, then it will be captured and in spiral into the core. So this is essentially a binary capture process, very comparable to what Scott proposed for the creation of binary Kuiper belt objects through dissipation of energy with dynamical friction with small bodies in the outer disk, just as a historical note. So, so let me say that again. So we're bringing in what Pebble accretion does is it allows you to accrete planetesimals from a much larger cross section than you would do if you were just bringing this thing in and gravitationally focusing it onto our core, which is the classic way that you accrete in the absence of gas. Because gas drag is a dissipative process, then you can capture your planetesimal from a much larger distance. So I'm gonna say all of those words again, but with some pictures. So if you have a core with a Hill radius around it, a planetesimal in the absence of gas can in principle be gravitationally bound to the core within the Hill radius. But when you have gas present, then now you have an extra force that's trying to pull your small particle off of the core. And incidentally, this is called Pebble accretion, but these don't have to be pebbles. They could be like fluff balls. The key thing is that they feel enough gas drag to be bound to the gas. And that means they have to be relatively small. Okay, so it feels gas drag that's trying to pull this thing off of the core. So if gas drag generates an acceleration that's larger than the acceleration of gravity, then of course it can't be gravitationally bound to the core. And so we can write in the presence of gas a new critical radius, which we like to call the wish radius, just for wind shearing, but also for whoosh, because you're pulling things off of the core. And inside this wish radius, you can have your small planetesimal can in principle be gravitationally bound. All right, and Pebble accretion is the process of binary capture within that wish radius. So you have your small pebble, it comes in, it dissipates relative kinetic energy inside this radius. And if it can dissipate enough to become gravitationally bound before it leaves out the other side, then it will be captured. And as soon as it's captured as a binary capture process, then it'll feel a headwind from the background gas, and that will cause it to lose angular momentum and spiral in onto the core. So that second part happens fairly quickly. So once you're captured, you can expect to accrete. And again, this cross-section for capture can be much larger. I'm talking about 4 orders of magnitude larger in some cases than the cross-section you would get in the absence of gas. So this can really speed things up. Here is a numerical simulation of this process happening. This was done by Xian Zhu, who was at that time an undergraduate student, Zhuining Bai, and myself. Xian is in the process of applying for postdocs right now, showing this capture process happening in a simulation with realistic turbulence and so forth. So you can see the particles coming in and within a large cross section being captured and spiraling in. Okay, so maybe this is a moment to stop and ask if anyone has questions about those preliminaries. Okay, so I'm going to go on to talk about super-Earths. So in this context, super-Earths are a bit of a puzzle unless we add an additional piece of physics. And that is because if you get to super-Earth masses in the inner region of a planetary disk and there are pebbles around, you should be growing like gangbusters, given what we've just said. Pebble accretion is incredibly efficient. It's embarrassingly efficient. So to recap, in classical terrestrial planet formation, planets are limited by their available mass. We talked about the local isolation mass at the location of Earth is less than an Earth mass that gets enhanced by crossing orbits in a giant impact phase. But with pebble accretion, you're not limited by local mass. You're drifting small solids due to gas drag from the outer nebula. The amount of material that could be drifting through your disk, just given very reasonable parameters, nothing fancy, over a million-year lifetime of a protoplanetary disk is gigantic, much, much larger than an Earth mass. So there's plenty of material to work with. And if you look at the growth rates from pebble accretion processes, and all I want you to look at on this plot is the fact that, you know, somewhere at some, you know, reasonable, you know, sizes, this is actually out at 30 AU in the disk. In the inner disk, it's even more extreme. You know, at reasonable small pebble sizes, the blue regions here give you growth time scales that are less than 10 to the 5 years. You can grow just incredibly quickly if you have pebbles around. And there should be plenty of pebbles around drifting in from the outer disk. The other thing to see from this plot, though, is that it's incredibly size dependent, this process. If you get rid of all of the pebbles of this size and you only have really small things, then it slows down quite a lot. Okay, so we need, so in the outer disk, that's actually really important. In the inner disk, you probably have pebbles of the size that you need because they can grow pretty quickly. And so we need some process that can stop this growth. And there are two ideas that have been proposed. One is called pebble isolation and the other is called flow isolation. They both, in the inner disk, limit growth at a mass that's comparable to what's called the thermal mass. But I'm going to tell you the differences between these two processes. And the key thing here is that the thermal mass, which is what happens where your planet's atmospheric size, the disk scale height, and its Hill radius, which are all equal. And if you set two of those equal, you get the third is about equal as well. That mass scale is set by the aspect ratio of the disk and the mass of the star. So it's determined by the disk temperature. It is not determined by the surface density of the disk. So if you're in a situation where your growth is incredibly fast by pebble accretion, and you have plenty of pebbles around to allow for that growth, you expect your solids to grow up and hit a mass scale that is determined by your disk temperature not by your disk surface density. And I'll just point out that Yunshin Wu has recently interpreted a characteristic mass scale in the Kepler data as the thermal mass. So there is some observational evidence that this is an important mass scale. Okay, so what are these processes that are giving this, this limiting mass? Pebble isolation happens when your growing core raises, starts opening a gap, raises an overdensity in disk gas that prevents pebbles from flowing onto the planet. So overdensities in the disk gas change the direction of the pressure gradient that changes the relative velocity between the gas and the solids. And the upshot of that is that in pressure maxima in disks, these drifting pebbles want to slow down and get caught. So, so pebble isolation happens when, well, you get to a big enough mass that you raise a pressure maximum and everything that's drifting in from the outside gets caught here. Now this is a really nice model. One of the things I'm a little worried about with this is that as we saw, the mass flux that can be, the total mass that drifts through the disk over time can be quite large. So I'm a little worried about what happens when you capture an amount of mass in here that's comparable to your planet mass, and whether then this becomes a dynamically unstable situation. But if you can get around that, then this can stop you from growing by pebble accretion. The second process, which flow isolation, I'm going to talk about a little more because that's what we've been working on. And to do that, I'm going to go back again to this diagram that we showed before. So remember our wish radius, where gas drag can't pull off particles from our core, is the region within which you can accrete through the binary capture process of pebble isolation. Okay, but I mean of pebble accretion. But what happens if that radius gets smaller than the atmosphere of your planet? Well, the gas in the nebula is flowing around the planet. Now, it doesn't have to be flowing around, as Jeffrey knows, in this in such a nice, smooth way, but it has to get around the planet somehow because it's not accreting on the planet, or at least it's only accreting onto the planet slowly compared to this flow. And if you have a particle that for which the wish radius is inside this atmosphere of the planet, you can prove that that means that it is coupled to this gas flow on the scale of the planetary radius. So that means if the gas flows around, the pebble flows around too. So this result doesn't depend on the flow looking like this. What it depends on is that whatever complicated thing this is doing, the turning radius of the flow, or at least for most of the gas, is comparable to the size of the barrier that's put in front of it. And that's sensible because if you have a barrier, that's setting the scale for the flow here. So if you have, so your particle is coupled to the gas flow, then not only does it not get captured preferentially with this binary capture process at a larger radius, it doesn't get captured at all. So this is preventing things that would have been captured from being captured because they're going with the flow. So we call this flow isolation. And you can, if you can prevent all particle sizes from flowing around this atmosphere, then you can stop pebble accretion altogether. That won't prevent you from accreting like additional really large planetesimals if they're around, like, you know, kilometer size, 100 kilometer size things if they're around, because they don't care about the gas. But it will prevent you from accreting any pebbles. So this is flow isolation. So flow isolation requires that you get to about the thermal mass, that same mass scale we were talking about. if pebbles that are marginally coupled to the gas disk are present, which in the inner disk, is up to something like, meter sizes. That's the meter size drift problem. For smaller Stokes numbers, if collisional destruction prevents you from getting that large, then the flow isolation mass is smaller. So if you have a lot of collisional destruction that keeps all of your material small, then you're going to have an even smaller than the thermal mass flow isolation mass. Okay. So what if we try this? So this is just an example, but if you go ahead and choose a reasonable Stokes number for the inner disk, some reasonable disk accretion rates, and the reason that's important is because it sets the disk temperature. Remember, the disk temperature is what tells you what the mass is. Then we can plot some flow isolation masses, and it's quite easy to get them in the super Earth mass range. They can also get, smaller down to terrestrial masses if you have a cold disk. And you'll notice also that, this is pretty flat. So there is another observational result that says super Earths may have similar sized siblings from Lauren Weiss and Sarah Mulholland. And this could be a reason why you make similar sized super Earths in a given system. The flow isolation mass doesn't depend a whole lot on distance from your star. Okay, so just for any aficionados that might be out there, very briefly, flow isolation stops smaller pebbles more easily. Pebble isolation, that was that density raising, stops larger pebbles more easily. And so we've shown that, and we've also shown that flow isolation mass, so they can actually work together to make things stop all of the pebbles more easily than one or the other. Sometimes the flow isolation mass is less than the pebble isolation mass if the Stokes numbers of your particles are much less than 1. But if you're not an aficionado, you can come back and say that because in the inner disk, large pebbles are reasonably likely available. The upshot for both of these processes, whichever one you like better, I obviously like ours better, but that's neither here nor there, is that you're going to limit growth at the thermal mass or a bit lower. And that's set by disk temperature. Okay, so what does the thermal mass look like?
Ruth?
And yeah.
Question from Chris.
Yeah.
Hi, Ruth. Just maybe I missed it, but what is your definition of a pebble here? Sometimes a pebble is defined as having Stokes number equal to 1, so I'm just a little confused.
I am defining a pebble, thank you for asking, as anything with Stokes number 1 or smaller.
Okay.
If you want, it could be even a little bit bigger than that, but not something that has a Stokes number much larger than 1, so it's not going to be affected by the gas. So I don't want to define it as having any particular Stokes number, because my expectation is that you're going to have a particle size distribution in your disk. Probably the maximum particle size that's present in whatever either growth process or collisional cascade will have most of the mass if everything is kept less than Stokes number 1. But there is going to be a range of particle sizes, and they can actually all contribute to growth. So one of the things that we showed in this submitted paper is that if you, in pebble isolation papers, it's often talked about as just stopping the maximum particle size, but because pebble isolation stops larger pebbles more easily and the small ones can actually go through that pressure bump, you actually can get substantial growth even at the quoted pebble isolation mass just from the smaller particles in the size distribution if you pick something reasonable like a Donyani size distribution. So these processes are really size dependent, and I don't want to say that there's only one size present because I don't think that's realistic.
Okay, that makes a lot of sense. Thanks.
Cool. All right. Any other questions? All right. Okay. So what does the thermal mass look like in a protoplanetary disk? Well, here is a here's a, excuse me, here's a simple model that's illustrative of a disk, and this is done by Cassandra Anderson, who you know, for an example disk that shows the thermal mass for the accretion heated region of a disk. And then once you get out far enough in the disk that it becomes irradiatively heated, the thermal mass starts increasing. So because it's set by disk temperature, it depends on properties of the system, like you know, the luminosity of the star, the accretion rate that sets your accretion heating. And so you can get systems where in that inner region, you have large thermal masses that are above the critical core mass for gas giant accretion. You know, that in and of itself is, of course, a large topic of debate, what exactly that critical core mass is. But for the sake of argument, let's just say it's above the nominal value of 10. And you can get a set of gas giants. Or you could get in a very cold disk, a set of terrestrial planets, or you can get in the middle super Earths. And what I'll show at the end of the talk is that Cassandra's run some proof of concept calculations showing that making gas giants, if you take a distribution of disks, is rare. But when you do, you can get actually a series of multiple gas giants all at once. Most of the time, you're going to make super Earths or things that are smaller. So I'll show you those calculations at the end. But the key thing here is that making gas giants is rare, but when they form multiple gas giants is common. And that's going to bring me into the second and last major idea of this talk, which is we said at the beginning that, or at least I said, that I thought that those gas giants in the inner disk had eccentricities because they were excited by some dynamical process that had to do with multiple gas giants being present. But we know that gas giants are not, that they are much less common around stars than super Earths. So why would it be that it would be rare, but when you have them, you know, there's a big dynamical interaction because there are several of them? Well, this might be a reason, right? So you can make gas giants uncommonly, but when you do, have enough of them around to have a big dynamical upheaval to get those eccentric systems that we see. All right, so that leads me into talking about gas giants. So I'm gonna slightly shift gears here if there's anything anyone wants to bring up before I do. All right, so what happens if you take a bunch of gas giants and you put them in the inner part of a planetary system? And well, inevitably what happens is that they collide. Boom. This is, you know, anyone who does an n-body integrations and puts a bunch of gas giants in the inner parts of planetary systems knows that they'll collide, and I'll explain why in a second. So what if we take that seriously? What if there really is a giant impacts phase for gas giants? Right? There's a giant impacts phase for terrestrial planets that leads to the final growth of the Earth in classic planet formation theory. What if that happens for gas giants? I don't know if this is true. I don't know if this is right, but I really like it because it does some really nice things that you'll see, which is that we can make some pretty generic assumptions and get some nice agreement with the data. So if you'll let me make this one weird proposition, which is that maybe in some systems you start with a bunch of gas giants in the inner, several gas giants in your inner regions, not like 2. You have to have a few, 5 gas giants in the inner regions, which is weird. I totally agree. If you'll then we'll follow that and see where it goes, and you can see what you think. All right, so what if there's a giant impact space for gas giants? Okay, so if you put a bunch of of gas giants in the inner system, then, and they're close enough to each other that they're dynamically unstable, then you'll have a planet-planet scattering situation. So here's a nice animation from Eric Ford showing what happens if you have planet-planet scattering. Here, our planets are getting too close to each other, and whoops, somebody gets lost from the system. So this is typically what we think of with planet-planet scattering, right? Somebody was ejected, and somebody else was left behind with an eccentric orbit. And part of the reason that we think of that as the outcome of planet-planet scattering is because of giant planets, is because giant planets in our solar system are in the outer regions of their planets, of the planetary system. So we think of, in the inner regions, you know, we have a giant impacts phase for terrestrial planets, and in the outer regions, if you had planet scattering of gas giants, and maybe there was an extra gas giant in our system, it's hard to know in the past, then it would lead to ejection. But it's really not about terrestrial planets and gas giant planets. It's about if you're in the inner system or if you're in the outer system, right? So if you're in the inner system, what's going to happen is you're going to get collisions. So why is that? That's essentially, and I'll go through it in a little more detail, because in the inner system, you have a deeper potential well, so it's harder to be ejected during these interactions. Okay. So the idea here is that in situ scattering plus collisional growth of multiple gas giants in a population of disks can produce features of the observed giant planet population. And Cassandra has also written some very nice work on this. On the scattering in the inner system, producing the observations. Okay, so close-in gas giants are often a whole lot more massive than Jupiter, right? They go up to 15 Jupiter masses. So if I'm going to start with a bunch of small gas giants and collide them to make something big, small can be Jupiter mass. It doesn't have to be that small. They're up to they're giant. They're 20 Jupiter masses. 15 Jupiter masses, mostly larger than Jupiter. So I'm going to start with a bunch of like small Jupiters, by which I mean Jupiters. They're not actually small. Okay, their orbits are often eccentric. I said this before, but here is a plot. So this is semi-major axis versus observed eccentricity, and I'm going to show a bunch of contour plots here, and they're all going to be percent contour plots. So this is a 90%, 80%, 70%. So they're percentage contours, so you can compare them one to another. And you can see that a lot of them are eccentric, which we know. And there are a lot of ideas for why this is. There's a long, we're thinking about planet-planet scattering, which has a long history, and we're drawing a lot on ideas from, for example, Urich and Tremaine. Okay. So planet-planet scattering leads to collisions for close-in planets and ejections for distant planets. So why is that? So if we think about an encounter with a relative velocity less than the planet's escape velocity, then you end up with gravitational focusing happening. So your cross-section for strong scattering is going to be larger than your cross-section for collision. And so the most typical outcome of this sort of encounter is a scattering. Whereas if your relative velocity is larger than your escape velocity from your planet, then you don't have any extra scattering cross-section, and instead you're most likely to collide. Collisions prevent strong scattering in this case. So what are we talking about in terms of relative velocity for these gas giants? Well, they're on Keplerian orbits. So we can think of the relative velocity of encounters as something like the eccentricity times the circular Keplerian orbital velocity. And that just comes from epicycle theory, right? You think of an orbit as being, you're going around on a circular orbit, plus on top of that, you've got an epicycle. Because it's a closed orbit, it's Keplerian, you go around your epicycle once, and the radius of your epicycle is something like your semi-major axis times your eccentricity. So that means your velocity on your epicycle is something like your eccentricity times your semi-major axis times the angular frequency of going around the star, again, because it's a closed orbit, So we relate our relative velocity to the eccentricity in this way. So what that means is that if to get that strong scattering to excite each other's eccentricities, we need the relative velocity to be less than the escape velocity from the planet, which corresponds to the eccentricity being less than the escape velocity from the planet divided by the Keplerian velocity. And if you reach this eccentricity, then collisions set in and you stop exciting orbits. So, however, you'll get system escape if your relative velocity is greater than the Keplerian orbit, just because now you're moving faster than the Keplerian orbit. You're going to leave the potential well. This is about the escape velocity from the star. So if your escape velocity from your planet is larger than your Keplerian velocity, you expect ejections. And to summarize that, you'll get in the outer planetary system, it's easy to escape from the star. You'll get excited to the escape velocity from the star before you start colliding. Whereas in the inner system, that won't happen. You won't be able to be excited to the escape velocity from the star. Instead, you'll start colliding. And that's just because it's harder to get out of the star's potential well. And the escape velocity from our planet here is a little different between gas giants and terrestrial planets, but it's not that different. So again, whether you collide or eject doesn't have to do with what kind of planet you are. It has to do whether you're in the inner system or in the outer system. So if you have a bunch of gas giants in the inner system, they will collide. Okay, so if you go ahead and look at, again, that observational eccentricity versus semi-major axis that we showed, and put that bounding eccentricity as the escape velocity over the planet divided by that of the star, and it works reasonably well to bound the observed, for some median properties, to bound the observed data. And then again, in the outer system, you'll end up with ejections. Now, this isn't the only way to bound this edge of the observed population, but it's consistent. Okay, now here's the thing that really gets me, though. High eccentricity giants are also higher mass. This looks like the same plot, but it is not the same plot. This is now mass of our planet, and this is the observed eccentricity. The higher mass gas giants, the really big ones, are the ones that have the high eccentricities. And that's super weird, right? Because it should be easier to excite the low mass ones to high eccentricity. And in fact, if you put a bunch of planets together that have different masses, that's what will happen. The low mass ones will get excited to higher eccentricity. They're more easily perturbed. But that's not what we see in the data. So why are the higher mass ones higher eccentricity? And it gets more interesting. Planets with the highest eccentricities are not just the giant planets, they're also the ones around the highest metallicity stars. So high metallicity stars are the ones that make these large high eccentricity planets. I'm going to plot this back in semi-major axis space, and this is just observations. This isn't theory at all. So this is observed eccentricity versus semi-major axis, and if this is a cut on metallicities of stars greater than or less than the sun, and you can see the blue ones, the high eccentricity stars, just have a higher envelope here in terms of how high eccentricities you get to. Okay, so we have high metallicity stars. They're making more massive planets. They're making that have high eccentricities. So what might that be? So maybe the high metallicity stars produce a larger number of massive planets, and in those disks, all the planets are excited to high eccentricities through planet-planet scattering. So in other words, how high an eccentricity you get to is not to do with your own mass, it's to do with your neighbor's mass. And your neighbor's mass is correlated with your mass. And if you have a whole bunch of high mass planets together, they will get to these high eccentricities. All right, I am running short on time here, which is fine. So I'm just gonna skip through the details of our numerical simulations here, but I wanna point out a couple of key things. So we've done some n-body simulations. we're doing a collisional growth phase of giant planets. We have to put in an appropriate mass radius relation as the planets grow. Because remember, the escape velocity from our planet is critical to how much it can excite its neighbors. I can start with a whole bunch, and we're going to start with a bunch of planets in each system, you know, sort of evenly spread out. It doesn't matter how many planets we start with, it turns out. It just matters the total mass of planets. This makes this a very nice thing, as long as we have several. If we have 5, or if we have 50 planets, I'm going to get the same answer as long as they add up to the same mass, because they're all going to collide and grow and end up with just a few. So I'm putting in a bunch of planets, small planets. Remember, small planets are Jupiters. And I'm going to assign the ones with the most total mass in planets to be high disk mass. I do work on disks. This has nothing to do with actual disks. I just couldn't come up with a nice, clear name for total mass in gas giant planets. That's what I mean by disk mass for the next 3 minutes. So I'm going to assign the high disk mass ones high metallicity, just for the sake of argument. And then here's the only fine tuning we do. We tune our disk mass distribution to match the observed planet mass distribution. So given the total disk mass, we end up with some characteristic maximum planet mass. And so we generate a distribution of disk masses that matches the observed planet mass distribution. This is the only fine tuning in this whole thing. Okay. And here are the results. So here is that mass versus eccentricity for the RV observations. And here's the result for our simulations. So we see the high mass planets have the high eccentricities, and they get up to those high eccentricities that we like. And you know, these don't match exactly, but again, I only fine-tuned that, or well, Renata Frelich, who is the graduate student who ran these simulations, only fine-tuned that one thing. We can, if we assign those metallicities, then again, the high metallicity, the high disk mass ones are the ones that produce the high planet masses and the high eccentricities. We look up at the top there. And if we go back to semi-major axis versus eccentricity, you know, these envelopes look okay. And again, we get this metallicity feature in our outcome that comes from a range in disk masses. And the overall distribution, which I haven't shown here because I've broken it up into the two, but you can see just by sort of adding them up by eye, looks very nice, and it goes up to the appropriate high eccentricities, gives a reasonable range here. So again, this is not fine-tuned, which is why I like it. Okay. Higher mass planets are found more frequently beyond 0.3 AU. Here's the observations, the simulations. I could talk about that more if you're interested. On a larger scale, eventually scattering starts dominating. And so you end up with a peak in the mass distribution. This is what it looks like for an individual disk mass, collisional growth and scattering. And if you do our distribution of disk masses, the peak mass of the planet that you get, not the number of planets, the peak mass is maximum between one, you know, at a few AU. So this is a clear observational prediction of this kind of model. The most massive planets should be found at a few AU. And if you go to larger distances in your disks, you shouldn't make planets that are quite as massive. So this region is probed by radial velocities. You get these high mass planets. Direct imaging probes these regions. It's sort of limited to 2 Jupiter masses, which is above the typical mass that you'd expect in here. And there are a lot of future observations that will help look for this. Okay, so the idea here is that high metallicity stars produce many massive planets that are excited to high eccentricities. So we're going to predict a population of high mass gas giants in this region of collisional growth based on this idea. Okay, So we can do a population analysis of different disks to see, well, do you get a reasonable number of these sort of gas giant systems versus lower mass systems? And here's the last idea, because I know I'm out of time, which is that higher metallicity stars could produce more massive disks, but they could also produce higher opacities, which lead to higher temperatures in an accretion heated disk that leads to higher thermal masses, resulting in gas giants. Okay, so I'm just going to flip through this, but Cassandra's been able to proof of concept that we can get a reasonable gas giant versus super Earth mix. We can get reasonable super mixed versus gas giant systems, and we can get gas giants being more common around more massive stars. So this is the proposed story. Planets grow to flow and or pebble isolation. If the cores are big enough to accrete gas, you get multiple gas giants, and then they scatter and collide, producing high mass eccentric giants. So I'll end there. Thank you.
Thank you. Any questions? I have a question. Is there enough gas in the inner parts of the disk to form multiple gas giants?
There, at any one given time, no, but if it's an accreting disk, then if it's gas accreting from the outer system, yes.
Presumably they have to wait very long for that though, so they could become unstable before they can wait a couple million years for all that gas to come in.
Well, so it's, yeah, right. So it'll depend on whether the gas that's around them is providing enough damping to stabilize them. But they can also be unstable and start colliding with each other as long as you, I mean, so I agree that that's a question, and I don't know the answer to this. Oh, and I'm talking right now. I'm sorry. It's a question that I don't know the answer to because it's going to depend on the details of the gas damping. But I'll just point out that for this gas giant story, you don't necessarily need to form them in situ. You know, you can migrate in your gas giants if you like for that half of the story. I just like the connection to the thermal mass and flow isolation, because it gives you a reason why you would rarely produce gas giants, but produce many at the same time.
Question from Jeremy.
Thanks for a really nice talk, Ruth. You covered an awful lot of ground. It provokes many questions, but I'll just ask one. How might all of this apply to the rings that are seen in the D-sharp disks, which many people interpret as evidence of planet formation, maybe in the sort of above super Earth but below Jupiter mass range, out at many tens of AU very early on? Yeah, on nearly circular orbits?
Yeah, great question. So I don't know if those rings are planets, but let's say they are for the sake of argument. If you look at the flow isolation mass out at those large distances, then it depends quite a bit on what Stokes number size of particles are available. So in the inner disk, I feel reasonably comfortable saying, well, you're going to grow until whenever you start collisionally fragmenting, right? And so that's going to be something, maybe it won't be all the way up at Stokes number 1, maybe it'll be a Stokes number 10 to the minus 2, but it's not going to be a tiny Stokes number. Whereas in the outer disk, you're not limited by fragmentation, but rather by drift. So you grow until you start drifting. And so you can actually be limited to substantially smaller Stokes numbers. And that can cause, as you go further and out in the disk, your flow isolation mass to get smaller and smaller compared to the thermal mass. And so you can get reasonable flow isolation masses, you know, very far out in the disk that are of the mass scales that you're talking about that way. So that's something that we're working on, trying to couple those particle drift models to flow isolation to see whether you get a reasonable distribution of core masses. Now, if you, you know, in other circumstances, you can actually get very fast growth to larger masses in the outer disk, which might be, you know, why you might get unusual systems like HR 8799, which is fundamentally why I was originally thinking about Pebble accretion. But I think it might be the case, because of those limitations on the particle sizes, that smaller planet masses are actually the more common outcome. Did that answer your question?
Sort of, yes, thanks.
Next question, Elliot.
Hi, Ruth. You stressed the puzzle of how to explain why super Earths don't grow to be significantly larger than they are.
Yeah.
I've heard a number of talks that one solution to that puzzle is that they form late when the gas is mostly depleted. So this is just for a non-expert. Could you kind of give your perspective on that solution versus the solution you gave? Thanks.
Yeah, so the minimum mass that you need to get to before a pebble accretion kicks in is quite small. In the outer disk, you need to worry about it, whether you can actually get to that mass. But in the inner disk, it's very easy if you have any sort of planetesimals around to get to a mass where pebble accretion will be outrageously effective and cause you to grow incredibly quickly. So I think that if you want to appeal to that sort of solution that you're talking about, you need to also argue that the pebbles that you need for pebble accretion are not there. And maybe that's true, but I find it puzzling because it seems hard. It just seems very hard to me to get rid of them.
Okay, thank you.
And they're observed in the outer disk where they're harder to form. They're directly observed at these sizes.
Last question, Scott.
So if you do have giant impacts between Jupiter size and larger objects, is it clear that they'll retain the gas envelopes?
No, it's not. These are very high energy impacts. So I've heard from a couple of people working on hydro simulations of this that they think that tidal dissipation will actually cause the planets to coalesce, but I haven't seen any of that work published. And there's definitely enough energy around that I'd be worried about it. I'm sure that they're not, perfectly efficient coagulation as we did in these simulations. So I think that's a good question.
All right, thanks, Ruth, again for a wonderful talk. We have a call lunch in about 24 minutes, so hopefully everybody can get some food. We'll see each other soon. But call lunch is a different link, so check your email, don't come back here.